Welcome to RISE Learning Machines seminars, everybody. Today's seminar will be slightly shorter than usual. We have 45 minutes, and then Fredrik has to be somewhere else. So there will be a talk of around 30 minutes and then some discussion after that. So today, my pleasure is to introduce Professor Fredrik Lindsten from Linköping University. Fredrik has a PhD in automatic control from Linköping in 2013. He was a postdoc at University of Cambridge in 2014 and 2015. He's been a visiting researcher at SAIL in Berkeley and at University of Oxford. And among his research interests are probabilistic models, uncertainty quantification for machine learning, computational statistics, and signal processing. Today's topic is uncertainty in machine learning.
Okay, so first two small corrections perhaps from the introduction here. That first, I'm not professor, but associate professor. Or I think I heard yesterday that the official translation out of Linköping University is senior associate professor. But, anyway, but then maybe the more important correction is that I do need to leave a little bit before 4, but I actually managed to sneak away from the office and I'm at home now. So that means that I have a few more minutes. So you shouldn't feel that you can't ask questions and so on. So I think we will have plenty of time for the discussion, hopefully. Okay, so I will talk today about uncertainty in machine learning. And the talk will be essentially consisting of 2 parts here, where in the first part, I will introduce this notion of calibration, which is really about evaluating the reliability of uncertainty estimates produced by a machine learning model. And this is based on 2 papers, in particular this second paper here that was published at ICLR last year. And this is joint work with my PhD student, David Wiedman, and also his co-supervisor, James Zachariah. And then in the second part, we will look at another aspect of uncertainty quantification, which we call weak supervision, which is about learning from noisy training data, you could say. And this is based on a recent publication from AI Stats this year, together with my other PhD student, Amanda Olmin. Okay, so we will work with predictive models in this talk. So that is kind of the core of machine learning models, right? That we have, we want to learn a model that can take some input data X and compute some corresponding prediction of a target value Y. So as an example, we can look at this case with skin lesion classification that was published in Nature a few years ago, where the input data is an image of a skin lesion. So this is our input X. And we feed this into some computer program, like a neural network, that does some number crunching on the pixel values in this image and outputs a prediction of what type of lesion we see in this image. So in this example, we have a multi-class classification problem because we have sort of a predetermined set of possible lesions of possible classes, and we want to determine which one they're in. And the typical way of training such a model, as you probably know, is using supervised learning, where we have collected some kind of labeled training data set, so pairs of inputs and outputs. And then we train our model by feeding our input images to the model. It produces some prediction, and we can then compare this prediction to the actual annotated labels in the training data. Typically using some loss function. We then have a learning algorithm that is responsible for updating the model parameters to make the predictions closer to the training data. Right, so in many situations, we're not only interested in producing predictions of this target value, but we're also interested in having some notion of the reliability or the uncertainty in these predictions. And to this end, we will turn to probabilistic predictive models. And what I mean by this is simply that the model is asked not only to produce a prediction of the target Y hat, say, but actually a full probability distribution over possible targets. I will denote this probability distribution by Px here. So this is essentially an approximation of the conditional distribution of the target Y conditionally on the input X. So for classification problems, this is actually the standard way of doing things. A typical classifier will output a probability vector over all the different classes. So formally, that means that our model Px is a function from the input space to the k-1 probability simplex, so that the kth element then of this probability vector is an approximation of this corresponding class probability. However, this notion of probabilistic predictive modeling can be generalized to other problems as well. So for instance, for regression, we could assume that the conditional distribution of the target given the input is Gaussian, with some mean mu and some variance sigma squared that depend on the input x. And in practice, I mean, if we would train say, a neural network for this, the actual output from the network would, of course, then be the conditional mean and the conditional variance of these two functions here. But conceptually, we can view this as predicting a probability distribution over real numbers with this Gaussian assumption. And this idea can be generalized to arbitrary output domains and arbitrary probability distributions. So as an example, if we would have, say, some count data as our target variable, we could do something similar to a Poisson regression by having a neural network model parameterizing the rate of a Poisson distribution. And the way we would typically train such a probabilistic predictive model is by maximum likelihood, or by minimizing the negative log likelihood over the training data set. And that for classification is equivalent to the well-known cross-entropy loss, but we can generalize the same idea to arbitrary problems. Okay, so with that introduction, I'll turn to the first part of the talk then, which is about calibration evaluation and calibration errors and tests. Before moving into this, if you have any questions, feel free to interrupt me at any time. Okay, so assuming now that we have such a probabilistic predictive model, for this to be useful, for this to actually add any additional value to just predicting a point estimate, we need these predicted probabilities to be reliable in some sense. We want the probabilities reported by the model to be consistent with the empirical frequencies of observed outcomes. And this is a property that we refer to as reliability or calibration. And I would say that this is a central concept for quantifying predictive uncertainty, and also crucial for robust decision-making, in particular when it comes to safety-critical systems. So formally, we define this concept, this notion of calibration, in the following way. So we say that the model, Px, again, remember that this is a probability distribution over targets y. We say that this model Px is calibrated if this condition holds almost surely. So I use this operator here, law, simply to describe the distribution of some arbitrary random variable. So this is simply the conditional distribution of the target conditionally on the prediction. And the model is calibrated if this conditional distribution agrees with the prediction. So this is just sort of a mathematical way of writing what I said on the previous slide here, right? That knowing the prediction of the model, we expect the actual empirical frequencies to agree with the prediction in the long run, the predicted probabilities. It's worth emphasizing here that calibration is sort of a complementary property to performance. So to see that, we can look at the two extreme cases. First of all, if we consider the optimal model, which is such that our predictive model is exactly equal to the conditional distribution of the target given the input. So this is the optimal base classifier in the classification setting. Then this model will be calibrated. But so will the constant model, which simply disregards x and always predicts according to the marginal distribution of y. So both of these models are calibrated. The latter is, of course, not very useful in practice. But if you think about it, if you always predict according to the marginal probabilities, at least your probabilistic prediction is going to be reliable in the sense that in the long run, we expect it to be correct on average. Okay, so this is what we mean by calibration of a probabilistic predictive model. So how do we evaluate this in practice? Well, the most classical way of doing this is to do a visual inspection of calibration. And this applies to binary classification problems, so maybe the simplest possible situation. So for a binary classification model, we can let this probability distribution Px, or we can associate this simply with a number in the interval 0 to 1, which corresponds to the predicted probability of the positive class. And our calibration condition then reduces to requiring this identity here. But this function R of P should be equal to the identity function, where this function R, the so-called calibration function, is defined to be the probability of the positive class conditionally on that the prediction is equal to P. So if we would have access to this so-called calibration function, we could plot this in a reliability diagram. That means that we have the predicted probability on the x-axis, and we have the observed frequency or the reliability function on the y-axis. And the ideal model will then be one which follows the diagonal here, identity function. And if we would get something which is a bit skewed, like this red curve here, that will typically be an indication of overconfidence in the predicted probabilities. Right, so for a reliability diagram like this, we can of course equivalently look at the deviation of this curve from the diagonal here by simply subtracting P from this function, and we'll then end up with a plot looking like this. So now I plot the deviation RP minus P, and the ideal model then will be constant equal to 0. And this is the type of reliability diagrams that I will show you in the coming slides here. So ideal model, calibrated model will have a deviation of 0. Okay, so let's have a look at what this might look like in a practical example here. So here we train one of these good old LeNets from '98 on the C410 dataset. So it's a small neural network. It's used here for multi-class prediction problems. We have 10 different classes. I just said that these reliability diagrams, they only apply to binary classification. And in order to use this for a multi-class classification problem like this, we need to in some way reduce it to binary classification. And the way I do that here is that I consider the maximum prediction versus all the rest. So what I plot here now on the x-axis is not the probability of like positive class, because that does not exist, but instead the maximum prediction. So it gives one sort of notion of calibration, at least calibration of the maximum probability prediction. The second thing to note is that in practice, we of course not know this calibration function, so we can't just plot it. So what we need to do in practice is to estimate it from data. And this essentially boils down to computing a histogram-based estimator. So what I do is that I split this interval 0 to 1 into, in this case, 10 equally sized bins. I then look at all the predictions falling in one of the bins and compute the accuracy for those samples. And as I said, ideally, we should then end up with a deviation here, which is constant 0. Right. So at first glance, looking at this curve that we get for this LeNet, it might look like, well, it's pretty close to 0 up here, but then there's a sharp drop, which could then lead us to think that, well, this model is clearly uncalibrated because it deviates a lot from the ideal 0 here. However, the reason for this sharp drop is actually that it's based on this histogram-based estimator, right? So if we also consider the number of samples in our validation data set that actually fall in each bin here, we see that there are very few samples in these low probability bins. which results in a very high estimate, high variance in the estimate of this reliability function or the calibration function. So in order to interpret these reliability diagrams, it's important to also take some notion of confidence into consideration. And what has been proposed in the post and what we also recommend is to compute so-called consistency bars. So I won't go into the details of what this means, but they can be viewed as a way of visualizing the expected variation under the null hypothesis that the model is calibrated. So this is how much we expect the curve to vary if the model is calibrated. And if we do that here, we can see that we actually fall within these consistency bars for most of the samples or most of the bins. Another way of improving this reliability diagram is to have a data-dependent binning. So instead of taking equally sized bins, we can try to take the bins over this interval so that we get roughly the same number of samples or validation data points falling in each bin, and then we can reduce the variance. But even if we do so, it's important to also complement the curve with the consistency bars to get an idea of how much we expect the curve to vary. Okay, so this is the result we got for this LeNet model. Just as a comparison, I can also show you what we get if we instead train a larger neural network, so a ResNet 34 on the same data. And plotting these reliability diagrams, we can see that it's actually quite clearly deviating from constant zero, even with the consistency bars taken into consideration. So here we get some fairly strong support that this model is indeed overconfident in its predictions. And that's in agreement with what has been found previously, that large neural networks tend to be overconfident. Okay, so these reliability diagrams, I think they're very useful, and they provide us with a visual inspection of the calibration of the model. But they also come with some shortcomings, of course. And maybe the most important one is that they are very difficult to generalize to the multi-class setting. As I said, we can try to look at some kind of induced binary classifier, like comparing the maximum prediction against all the rest, something like that. But that in general is not enough to guarantee that the full model is calibrated. And I think in many situations, in particular when it comes to safety critical applications where we are particularly sort of interested in uncertainty quantification, we are actually interested in the low probability predictions. So if you think about the autonomous vehicle and you have some kind of system predicting the probability of an accident, then we are actually interested in the difference between the probability 1% or 0.1%. And another challenge is if we are working with something which is not a classification problem at all, say a regression or some other type of prediction problem, then it's difficult to generalize these curves. And furthermore, these histogram-based estimators that we use, they are random because they're based on validation data, and they are biased and even inconsistent in many cases, which means that it can be difficult to interpret and compare different models. And furthermore, it does not really provide any quantitative evaluation since it's mostly a visual tool for inspecting the reliability. So to address these issues, for the remainder now, I will instead focus on calibration error measures and how we can estimate them and use them for hypothesis testing. So a calibration error is simply some number that measures the degree of miscalibration of a model. And the arguably most common calibration error is this so-called expected calibration error, the ECE, which is defined as the expected value of some distance d between this conditional distribution of y, given the prediction, and the prediction. So D here is some distance on the space of probability measures over Y. So typical choice is the total variation distance, but it can be some other distance as well. And if you recall the calibration condition that we had, we said that the model is calibrated if this conditional distribution agrees with the prediction. So that means that the ECE will be 0 when the model is calibrated and positive otherwise. So the good thing with this calibration error is that it's kind of intuitive. It directly measures the distance or the average distance between this conditional distribution and the prediction, or in terms of the reliability diagram, you can view that as directly measuring the distance between the calibration function and the identity function. The drawbacks with this calibration error, however, are that it depends explicitly on this conditional distribution up here. Conditional distribution of the target, conditionally on the prediction. And this we don't know in practice, so we need to estimate this. And again, this means that we typically need to resort to some histogram-based estimator, which is going to be biased and even inconsistent. And it will not work very well in high dimensions. And a final issue here worth mentioning is that this error does not really have any meaningful unit or scale. So even if I would have some oracle that could actually compute the true calibration error here for a model, and that would report a number 0.1, it's kind of hard to say, is 0.1, is that large number or a small number? Is the model well calibrated or not? But to show you in a simple example here, some of the issues in particular related to what I said here about the bias and inconsistency. I've constructed a synthetic classification example here. I won't go into the details of how I generate the data, but it's sufficient to say that I simply generate some predictions and then I generate corresponding targets. And I do this 2 times. In the first case, I construct the data, so by construction it is calibrated. And then I have another data set which by construction is uncalibrated. And then I compute the ECE estimate for different distance measures. So here we are working with probability distributions over these 3 classes. So probability vectors on the unit simplex. So that means that I can just compare these probability vectors using, say, Euclidean distance, squared Euclidean distance, and we also consider the total variation distance. And then we also have a varying number of bins in the histogram-based estimator. And if we then plot all of these numbers that we get side by side like this, at least to me, it's actually quite difficult to see the difference between these 2 plots. Sure, if you look at it carefully, you can see that the uncalibrated model tends to have slightly larger values. But the difference is actually much larger as we vary the number of bins or change the distance measure. And if I would remove the titles here, so I wouldn't say which one is calibrated and which one is uncalibrated, I think it would be quite difficult to sort of come to the conclusion that here we're working with one calibrated model and one uncalibrated model. So in order to address some of these shortcomings, what we propose in this paper that I mentioned that was published at ICLR last year is another class of calibration errors that we refer to as kernel calibration errors. So the definition is a bit more involved, you could say, but I'll sort of talk you through it. And it's also, in some sense, a bit intuitive, I think. So what we do here is that we look at the supremum of the difference of 2 expected values. So first, I take the expected value of some function h, which depends on both the predicted probability distribution and the actual target. And then I take the difference from the expected value of the same function h, which is now evaluated at the same prediction, the x, and an auxiliary random variable z, which is constructed in such a way that conditionally on x, or actually conditionally on px, it is distributed according to px. So that means that this pair, P, X, and Z, they are by construction calibrated. And that means that if the model is calibrated for Y, then the pair of random variables appearing in these two expected values here are identically distributed. And that means that the difference will be 0. If the model is not calibrated, there might be a difference here. And then in order to sort of detect this difference, we take the supremum over so-called witness functions, H here. So kind of try to find a function which amplifies the difference as much as possible. And the supremum here is taken over functions in a unit ball in the reproducing kernel Hilbert space of some kernel K. So this is kernel K is a user choice. So kind of search in this RKHS for a function that makes this difference as large as possible, and that will be our kernel calibration error. And as it turns out, even though this definition looks a bit problematic perhaps to work with directly, we can do some sort of modifications of this expression. And for those of you who are used to working with kernels, and in particular, if you know about the MMD, the maximum mean discrepancy, then you might not be surprised that we can rework this expression and end up with something which is expressed instead directly in the kernel K that we can evaluate. And in particular, we can compute or find an equivalent expression here which does not depend explicitly on this conditional distribution, which was a bit problematic to estimate. And this means that we can construct both consistent and even unbiased estimates, not of the KCE itself, but of the square of the KCE. So this is the main benefit of working with this calibration error instead. Now, similarly to the ECE, it lacks any meaningful unit or scale, and we have sort of introduced another user choice here. Before we had to pick the distance measure and the number of bins in the histogram estimator. Now that is kind of replaced by the choice of kernel here. But still, if we do the same experiment as before, so I take this synthetic data set and I compute a bunch of squared KCE estimates now for different choices of kernels and different length scales in these kernels. So that would be kind of equivalent to the number of bins in the histogram estimator. And then the picture is a bit different. Now we get for the calibrated model, most values are very close to 0. Whereas for the uncalibrated model, for particular choices of kernels and length scales, we can see that it deviates a bit from 0, at least in comparison with the calibrated case. If we would take sort of a poor choice of length scale, either way too small or way too large, then this estimator will not really be able to pick up on the differences between the sort of the calibrated or the model and sort of the calibrated counterpart of the model. And this is due to sort of having a poor resolution essentially in our estimates when we take a poor choice of the length scale. But if we tune it appropriately, we can see a clear difference between these two models. And of course, in practice, you're free to produce a plot like this, right? And then it becomes more evident, at least in this situation, that this tends to or seems to be much more uncalibrated than this one. Okay, so in that way, we can use these squared KCE estimates or KCE estimates for model comparison. However, if we only have sort of a single model, I've trained a model and I want to know sort of is this model calibrated or not? We still face this problem that the estimate lacks any meaningful unit or scale, that just computing the KCE value doesn't really tell me that much. So to try to address this issue, we also took these estimates one step further and view them as test statistics for the null hypothesis that the model is calibrated. So in order to do that, we need to derive the distributions of our test statistics, and in our paper we have essentially different distribution estimates for the different estimators that we propose. But the most powerful one that we have found is an asymptotic test statistic, which is based on an asymptotic argument for one of the estimators conditionally on the hypothesis that the model is calibrated. This will converge to a particular value here. So without going into details, once we have this distribution, we can use it to perform hypothesis testing, compute p-values, and so on. So again, we can then look at our synthetic example and turning these sort of raw estimates of the calibration errors into p-values instead. And we get a similar picture that for poor choice of length scale of the kernel, the p-values are quite large even for the uncalibrated model, so we fail to reject the null hypothesis here as well. We can get too low resolution in the test. But for appropriately chosen length scales, we get small p-values, meaning that we can reject our null hypothesis that the model is calibrated. Whereas for the calibrated model, that is not the case, as expected, that we get fairly large p-values for all choices here. Okay, so this ends the first part of the talk then, and I think the take-home message here is that if you care about uncertainty quantification, then you should also care about this uncertainty quantification being reliable, and therefore you should make sure to evaluate the calibration. It's not something that we get for free. And in order to do so, I can highly recommend a Julia package that David has developed. It's called calibration analysis, and if you don't work with Julia, it also has wrappers for Python and R. And this package has all this functionality that I've showed you in the talk now, plotting the reliability diagrams with the consistency bars and so on, computing the various estimators, and performing the hypothesis testing. Okay, we can stop for a minute there and ask if there are any questions before I proceed with the second part. Okay.
A question?
Yeah.
In this example, you had like 3 classes, and in the previous slide, you mentioned that you could end up in trouble in cases when you are facing regressions and stuff like that.
Mm-hmm.
How does this work in the continuous domain?
Yes, I mean, for these calibration errors, for the ECE, it's also a bit tricky to move to the continuous domain, I would say, because it relies on histogram-based estimators. So you need to be able to bin your probability space, I mean, the space of probability measures in some way. What we do for the kernel calibration error is that we need some kernel operating on, kind of glossed over the details here, but the kernel here should be on this joint space of predictions and targets. If you think about the input to your kernel, it should be a probability distribution and a corresponding target value y. So what we do in practice is that, first of all, we split this into products of kernels, so-called tensor kernels. So we construct one kernel operating on the space of probability distributions. Then we have another kernel operating on the space of target values, and then we just multiply these together. And in order to construct the kernel on the space of probability distributions, what we typically do in say, a regression setting would be to, again, associate, say that we have a Gaussian regression. Similar to what I showed you in the beginning, we can associate this Gaussian with its hyperparameters, the mean and the variance. And those are the values that are actually predicted by the model. So then we construct the kernel on the space of means and variances, more or less. And we can kind of lift this to a kernel on the space of probability distribution. So it works, but again, I mean, it depends on how complex the domain of this probability distribution is, if it will work well or not, if it's easy to construct a reasonable kernel.
Okay, thanks.
So I had a question as well.
Yeah.
So forgive me for maybe a stupid question, because I'm very new to this subject. But this kind of uncertainty prediction, it requires the model to be specifically trained to output the probability distribution, right?
Yeah, exactly. So I kind of assume that we have a model which is trained to predict a probability distribution, right?
Are there any like complementary techniques that can be used post hoc on models that only predict like the actual prediction, like for example, a standard deep learning neural network for like a CNN or something?
Yeah, I mean, you can take that as your mean prediction, and then you can complement that with some prediction of the variance. I think that's also typically done in sort of standard regression, but then you would assume that the variance is constant,
right?
That it does not depend on x, and then it's essentially boils down to estimating a single sort of scalar value, and you can take your estimate simply as the error variance, like the residual variance on the training data. If you would want to have something more kind of sophisticated, where you can also take heteroscedasticity into consideration, meaning that the variance depends on the input x. What I would recommend would be to take your model, and then you, at some sort of intermediate layer, you add another sort of head to the model, which is responsible for predicting the variance. You can reuse some intermediate features, but then you have this additional sort of variance prediction head. And then you need to train that in some way.
Thank you.
But I guess, I mean, for classification and all of this, I think is highly relevant for classification as well. Then training probabilistic predictive models is the standard way to go, right? You usually train the classification model using cross-entropy loss, which is based on the predicted probability vector. So there you already have it in the standard setting. Okay, any more questions? Okay, let me then move on with the second part here, which where we take a slightly different sort of have a different look at uncertainty quantification or handling uncertainty in machine learning. So this is, as I said, based on a paper called Robustness and Reliability when training with noisy labels, written together with Amanda Olemin. And I should also give Amanda credit for the slides here for this part. I mostly stole them from her licentiate's presentation that she gave last Friday. So it's mostly Amanda's slides. But the setting that we consider here is that, or the problem that motivates this study is that in many applications, annotating training data can be both costly and time consuming, and can also be difficult in some situations. So there's a risk of incorporating faulty or noisy annotations in the training data, meaning that when we train our model, we do not have access to pairs of x's and y's, but instead we have the x's and some noisy version of y, which I denote by y tilde here. But the task is still to infer the distribution, the conditional distribution over y. So we're not interested in modeling this noise. We just want to use this noisy data to learn a model that can predict the actual label. So this is something that is sometimes referred to as weak supervision, and there are several solutions that have been proposed, or approaches to address this issue, from ranging from correcting and selecting the labels that we use for the training data to changing the model architecture so that it's more robust to the noise. And also what is most relevant for this talk now is to use so-called robust loss functions. So loss functions that are designed to be invariant to the label noise. What most of these previous solutions have in common, though, is that they mainly focus on robustness and accuracy. So we want models that can have high accuracy on clean data despite being trained on noisy data. So what we do in this paper is to analyze the effect of label noise, not only when it comes to accuracy, but also in terms of reliability. And we also compare or analyze sort of standard loss functions, in particular so-called strictly proper loss functions, where the usual concentric loss, for instance, is an example of a strictly proper loss. We'll compare the properties of this when trained with noisy data versus the so-called robust loss functions that are explicitly designed to handle noisy data. So in this part of the talk, I will specifically consider a classification problem. So again, we have assume that we have k classes, and our model is then a function mapping the input space to the k-1 probability simplex. So it produces vectors over probability vectors over these k classes. And here I will now make a slight change of notation and denote the model by f, but this is the same thing that I previously referred to as the px. So it's our classification model that outputs a probability vector over classes. And in order to train this model, we introduce a loss function that measures the discrepancy between the predicted probability vector and the actual target value. And the objective that we use for training is to minimize the risk. So that is the expected value of this loss with respect to the data generating distribution. And in practice, we would, of course, replace this expected value here with an empirical expected value, where we take a sum over the training data points instead and minimize the empirical risk. But for the purpose of analysis here, we will look at the asymptotic setting where we work with this actual sort of asymptotic risk. And I will denote the minimizers of the asymptotic risk with f star. So the minimizers here, because we could have multiple minima. These are the asymptotic risk minimizers. And of course, this applies if we have access to the clean data, the actual y target values. But similarly, we can introduce sort of a noisy risk by simply replacing y by y tilde, a noisy version of the label. And we get the noisy risk r tilde with its own sort of noisy risk minimizers, f tilde star. Okay, so using this notion of the asymptotic risk minima or minimizers, we can note that the label noise can hurt the model in at least two different ways. So first, it can result in a shift in the asymptotic risk minima, so that f tilde might be different from f. And furthermore, when we train this in practice using a finite sort of amount of training data, there's of course a risk of overfitting, and in particular overfitting to the noise in the labels. And this is something that we know it has been shown empirically that modern neural networks can actually fit completely random labels. Right. But in order to reason about these different ways in which we might suffer from the noise in the data, we will sort of conceptually think about the training of our model as consisting of two different phases. So first, so this should be viewed as sort of the model space, and we assume that we have some kind of iterative training procedure. So first, we have a convergent phase when the model kind of aims for its asymptotic risk minimizer. It aims for f star and approaches f star. And then we have a divergent phase when it starts overfitting, and it then sort of moves away from f star. So, but this is just sort of a mental picture. Right, but with this, we can then turn to our results. But in order to do so, in order to actually analyze this, we need some model for how the noise enters this model or this problem. And what we consider in this paper is a noise model referred to as simple non-uniform label noise, which means that conditionally on the true label or sort of clean label and the input data, the probability of observing a certain label in the noisy target here is going to be 1 minus some omega of x if y tilde is equal to y. So this is the probability. This is the probability of observing the true label, you could say. But with some probability, we flip the label to some other label, and that is done uniformly. So the fact that this is uniform over all the other labels is what makes this sort of a simple noise model. But at the same time, it is actually more, I would say, more realistic and more complex than most noise models considered in the literature, because it allows for an arbitrary dependence on x here. So most of the noise models considered in the literature, they assume that the flip probability is independent of x, whereas this can capture sort of input-dependent noise. And down here, we can see just an example of what this might look like. We have sort of 3 classes here with clean labels, and then we end up with a training data set with some corrupted labels like this. Okay, so turning then to our results, I should say. We start by looking at what happens if we train a model using a strictly proper loss function. And as I said, this is kind of the standard way of training a model. The usual cross-entropy loss is strictly proper. And what it means for the loss to be strictly proper is that it's uniquely minimized by the actual conditional probability distribution over the target given input. So that means that the clean risk minimizer will be this conditional distribution over the clean labels conditionally on x. And similarly, the noisy risk minimizer, f tilde, will be the conditional distribution of y tilde given x. So in our illustration here, this means that we will shift the risk minimizer. We will shift sort of the aim or the target point of the training from f to f tilde, if we use such a strictly proper loss function when training. However, we show then that even though we shift the risk minimizer, if we assume that we then compute predictions according to the most probable class of our model, then these two distributions here, these two conditional distributions, will have the same decision boundaries under the simple noise model, simple non-uniform label noise model. So put differently, even though we shift the risk minimizer here, this type of loss functions will be inherently robust in terms of accuracy. It will not change their asymptotic decision boundaries. However, if we instead consider calibration, then we also show that this noisy risk minimizer is typically not calibrated with respect to the actual conditional distribution of interest, that is the conditional distribution over clean labels. So we're robust in accuracy, but not when it comes to uncertainty quantification or reliability. So in order to maybe improve on this, we thought that, well, let's have a look at these robust loss functions, which are explicitly designed to be robust to label noise. And what we mean by a robust loss function is that it is invariant to the noise. Put differently, the risk minimizer for the clean data is the same as for the noisy data. And the definition that is used, for instance, in this paper by Gaussian here, is that the loss function is said to be robust if for all risk minimizers of the clean risk, they are also minimizers of the noisy risk. And in this paper, they also construct sort of a practical class of such robust loss functions that they refer to as symmetric loss functions that are provably robust to the simple non-uniform label noise. Right. So for these robust loss functions, we will also be robust in accuracy by construction. But in order to see what we can say about calibration or reliability, we then introduce something that we call calibration-based strictly properness. So we define a loss function to be calibration-based strictly proper if all of its asymptotic risk minimizers are calibrated. This is a weaker condition than requiring that the risk minimizers should correspond to the true conditional distribution, because there are many distributions that are calibrated. But it also guarantees that our risk minimizer will be reliable. And unfortunately, then we can also prove that these symmetric loss functions are not calibration-based strictly proper. So in principle, robustness is not sufficient for ensuring reliability. And furthermore, we also show empirically that although we have a robust loss function, we are asymptotically robust to the label noise, but in practice, this does not mean that we are robust to overfitting. So again, in our sort of schematic illustration here, robustness ensures that the target point here, when we train with clean labels or noisy labels, this will be the same. But we can still sort of deviate from here and end up with different models as we start overfitting. And in particular, when we train with the noisy labels, we can start overfitting to the noise. So in summary, the conclusion of this paper, which is, you could say, sort of a negative conclusion, but under this simple non-uniform label noise model, both the standard strictly proper loss functions and the robust loss functions are actually robust in accuracy. Neither is robust when it comes to reliability or calibration, and neither is robust when it comes to overfitting. So essentially, there is no additional sort of theoretical support for why we would prefer a robust loss function over a strictly proper one. So for future work, we propose to extend the notion of robustness to also include reliability. Okay, and that is my final slide. So thank you for listening. Are there any questions?
Question here, Fredrik. Thank you for your presentation. I was trying to understand this last work. Do you try to model the actual noise that is contaminating the labels, and then try to learn some modeling of this?
A good question. So, yeah, I mean, that is one approach to address this issue, that you actually try to learn what the noise, like the corruption model is. But that is not what we have done here. So what we are instead looking at is loss functions that are inherently robust to the noise. So regardless of what the noise realization is, they should in some way be robust to this. So no, we're not modeling the noise distribution, but that is also a common way of addressing this and an interesting approach, I think, to do this. And I think maybe in order to really come up with a solution that will also give us reliable models in the end, it's quite likely that we will have to do something like that.
Thank you. And the loss function that you are proposing that is robust to this noise realization, does it operate under the assumption that the noise actually gets averaged out unbiasedly throughout multiple realization during the training?
Yeah, essentially that's how you can think about it intuitively, yes. That you sort of weigh the error equally if you're on one side of the decision boundary compared to the other, and then in asymptotically they will average out.
Understand. Okay, thank you. I don't have any other question at the moment, at least.
Okay, thanks.
So you showed that the two different estimators should pass through the same optimal estimator. What if you use early stopping, sort of not to overfit to the noise? Is that?
Yeah, I mean, I think that in general that's something that we would recommend. Also, I mean, it sort of agrees with this picture, right? That we have first a convergent phase, and then you start overfitting, and then you want to use early stopping to stop as close as possible to this point. But that's kind of also one of our points here, right? That if you use a robust loss function, then you can end up maybe close to this point, hopefully. But there's really no reason for why you would prefer this model, this F star, compared to this F tilde star that you would end up with if you take a strictly proper loss function and simply ignore the noise. Because both of them will be robust in accuracy, but neither will be calibrated. But yeah, indeed, I mean, we want to sort of end up close to the risk minimizer, and that's why it's also relevant to study the risk minimizer. I think, I mean, the theoretical properties of the risk minimizer. But it can also tell us what we can expect sort of in practice when we optimize the empirical risk.
I have another question, if there is another.
Yeah.
I was just thinking, I'm sorry if it is a very stupid question, but is there any risk of, since we are following the labels more, like the focus here is like trying to follow the labels, even though they are noisy. And is there any risk that what we are generalizing here, it's mostly the annotator instead of the data manifold of your actual data? I don't know if that the question makes sense, what I'm thinking.
Yeah,
Because,
I mean,
I'm sorry, go.
Yeah, I think that is true. I mean, if we actually obtain this conditional distribution, then you are modeling the annotator. I guess you're always modeling the annotator in some way because you're trying to mimic what's in the training data. But it's true that if the annotator is sort of makes mistakes and we learn a model that mimics the conditional distribution of what's actually in the training data, the white tilde, then indeed we are also incorporating these errors in our model. That is true. But I think, again, the theory here says that even though that might be the case for the particular noise model that we consider, we can still end up with a model that performs well in terms of accuracy. And I think this is actually something that has been observed in practice, that even if you have, you make some kind of random label flips and you train a model, unless you flip very many labels, you will still end up with a reasonably good model, right? It will learn to generalize based on the clean data points.
Yeah, I understand that, because I was trying to understand what is the actual trade-off with this loss function that are robust in the long run from the noise.
Yeah,
that's.
Yeah, I mean the motivation for using a robust loss function would be to say that if I take a loss function that is robust, then I'm guaranteed to have an asymptotic risk minimizer, so sort of what we can at best hope to achieve when we train our model, which is independent regardless of the noise. Sort of, even if I would have clean labels, I would have the same asymptotic risk minimizer. But what I'm saying here is that, sure, you can have the same, but it's not necessarily very good, in particular when it comes to uncertainty quantification. So again, I mean, this is mostly in some sense a negative result, because we are kind of criticizing the use of robust loss function and saying that they don't really add any, they have little added value compared to just training using strictly proper loss functions. In theory, I should add. I think that there might be other benefits from these robust loss functions in practice, but that is kind of disconnected from the current theory.
Okay, understand.
I actually need to run pretty soon, so
okay, thanks a lot.
Like a quick final question, then I need to go. Realize that maybe my half-hour talk ended up being more than 45 minutes instead.
So I think perhaps we should let you go, and thank you very much for this talk and the nice discussion. Welcome back, everybody. Next week, May 19th, we'll have Marcus Livicki, Fredrik Sandin, and Carl Ekström from Luleå University of Technology. We'll talk about technical language supervision.
Yeah, and thanks for the invitation. And if anyone has a question that you didn't have time to ask now, just drop me an email and try to answer them.
Great.
Okay. Thanks. Bye.
Bye.